This here is a distillation apparatus. What I'm going to do is I'm going to show you all the different parts and how to work with them. Now, distillation is separating molecules based on the temperature that those molecules boil at. Well, for the Pepsi, as you can see, there's lots of different things within the Pepsi. We have the caramel coloring, there's sugar, there's water, there's the cherry flavoring, there's the cola flavoring, there's quite a bit of different things within the Pepsi. And I cannot pour Pepsi through filter paper and separate the molecules. I cannot separate them physically. So I have to separate them based on a different property of all of these molecules, which is the temperature they boil at. So if I'm going to be boiling Pepsi, I need a heat source for boiling these molecules. And this down here in the bottom is my heat source. This we can think of as a mini little candle. Now, the way it works is we have alcohol that we pour in this little container here, and then we have a piece of string that we use as a wick to draw the alcohol from the storage container up to the top. Now, if your wick falls out or you want to replace the string, what you can do is you can take a paper clip and use the paper clip to adjust the wick through the glass tubing. There are two types of alcohol you can choose. One type of alcohol is ethanol. Ethanol burns at a much higher temperature and releases a lot more heat energy than isopropanol. So you can choose isopropanol or ethanol, and there's advantages and disadvantages for each. Ethanol, if it is heating things up too much, you can actually boil all the molecules at once and then you're not separating them at all. If you use isopropanol, the challenge with isopropanol is that the candle might blow out and you'll have to relight it. But the trick is you want to separate the molecules. It's not about having the most intense flame, it's about boiling them at getting the temperature slowly raising up so that within your mixture different molecules will boil at different temperatures. Alright, so anyhow, what we have are lighters placed throughout the classroom. And all you have to do is push this little button forward, then you have the trigger, and then hit the trigger, and then you can light your candle, which will be your heat source. And it might take a little while for the thing to ignite, but once it does, you'll have a nice steady flame. Let's see if mine is lit. Now, the interesting thing about these little candles is that the flame, because it's alcohol that's burning, might actually be tough to see. It won't necessarily have a color to it. There we go. And I've got it burning now, and if I put my hand over it, I can definitely feel a lot of heat. So if you want to control how much you're heating up the Pepsi, you can adjust the distillation apparatus up or down to get the right amount of heat on your mixture. Now what we're going to do is we're going to take a look. I'm going to set the candle aside and leave it burning over here. We're going to take a look at the distillation apparatus itself. Within it are two glass containers. The first one, the outer one, has oil. Because we're not going to take the candle and directly heat the Pepsi, we're going to heat the oil. And the reason we're going to heat the oil is that we can very carefully get the oil up to higher and higher and higher temperatures without the oil actually boiling off itself. So the oil can take a lot higher temperature before it changes into a gas, which is a wonderful thing, and then we can heat our Pepsi, which will go in this container over here. And it's this inner container that's where the Pepsi will be. Now, within both these containers, you see these little rocks. Those little rocks are called boiling chips, and it allows very small bubbles to form should they ever form. And that's a good thing because we don't want too big of bubbles pushing the liquid up and bouncing the liquid around. So you're going to want to measure the volume of Pepsi that you place in this, and I do not think you're going to have to add any lime water to this. The Pepsi that will be out in the classroom is already flat. There shouldn't be any carbon dioxide in it. So don't worry about adding the lime water. That wasn't our procedures earlier. Now the Pepsi, you can add it about 3/4 of the way full. And then you're going to take it and attach it carefully screwing it into your distillation apparatus. Make sure it's tight. And then if you put the oil and screw the oil around, you want the oil actually surrounding the container with the Pepsi. So you can see I don't have enough oil. So I'm going to open up the oil container and add more oil so it surrounds the inner container with the Pepsi. I would have it about this full, and a good thing to do in science is always to measure what you're doing. So I'm going to take a ruler this time and measure how high it is, and it turns out that that's it's about, if I get it right at the 0 line, it's about 9.5 centimeters tall of oil. So now I'm going to screw it in, and you're going to see that the oil does surround the Pepsi, and this is ideal. This is what it should look like. So now you can position the alcohol right below it, and you can light your candle again. Oops, I'm going to move this to the side until I get my flame going. And the key thing to do is to consistently write down what you're observing. So you really want to get out that ruler and measure how far the flame is from the oil. Now what's going to happen is the heat source is going to, let me get it at about a centimeter, that's ideal. About a centimeter away, particularly for ethanol, should work. And the oil is going to heat up. And what you want is you want the oil to get at a temperature where only one molecule starts boiling. We can measure the temperature with this thermometer right here, and we can see that this thermometer is inserted into the neck of the distillation apparatus. So as different molecules change into gases, you can measure the temperature that they're coming off. Then, as the gas, say it's the food coloring comes off first. Well, it'll come off as a gas, and then hit these beads and then start to cool down. And as the gas cools down, it'll change back into a liquid, and then with a beaker you can collect it and observe the color, appearance, and odor. You can waft it towards your nose and smell it. So what's neat about this apparatus is that you can control your heat source, which allows you to adjust the temperature of the oil. What temperature the oil is determines what temperature the Pepsi gets to. What temperature the Pepsi gets to determines which molecules start boiling off first. Now this is where we're going to go to the whiteboard for a little bit, because we said that distillation is a process of separating molecules based on their boiling temperature. Well, what I'd like to do is I'd like to point out the possible molecules that you're separating out in the Pepsi. So for the Pepsi, there's a bunch of different things. We have water, and we know water boils at around 100 degrees Celsius. We have, say, the cherry flavoring. We have the food coloring. We have the cola flavor. And we might also have a little bit of the last thing I'm missing here. Miss Walls, what am I missing? What else is in a cherry Pepsi? We don't know what's in a cherry Pepsi exactly. That's their secret recipe, so who knows what we're going to see from this lab. Now, what if the cherry flavoring is a molecule that boils at 60 degrees Celsius? So this is not for certain. This is an estimate. If the cherry flavoring boils at 60 degrees Celsius, as your apparatus heats up, remember you have the two containers. This is where you have the Pepsi, and this is where the oil is. If you get this apparatus to 60 degrees Celsius, then the cherry flavoring will start coming off. And then you can collect just the cherry flavor. Then as you heat it up to 100 degrees Celsius, then what will start coming off is the water. So you can separate out your molecules based on the temperature that they boil at. So why do they have different boiling temperatures? Well, because these molecules have different structures with different intermolecular forces. Molecules that have a higher boiling point have strong intermolecular forces. Remember what we've talked about in class is that the stronger the intermolecular force, the more sticky the molecule is. Water molecules are actually incredibly sticky. And remember that water molecules stick to each other through hydrogen bonds because water is a polar molecule. So there's a lot of energy that's required to boil water molecules because of these intermolecular forces. That's an example of an intermolecular force. If you have a molecule that doesn't have a strong intermolecular force, it's going to boil at a lower temperature. Remember, if we're boiling, going from the liquid state of matter to the gas state of matter, liquids are actually sticking to each other with intermolecular forces. When you heat something and it changes into a gas, now the water molecules are moving so fast, they're not connected to each other anymore. And because they're not connected to each other anymore, they're not stuck to each other. So all the energy that you're using to boil your mixture is being used to break these intermolecular forces. So the stronger the intermolecular force between molecules, the more energy it's going to take to change that molecule into a gas. If you have any other questions, please ask Ms. Wallace or Dr. Brown. Thank you.